Hello everyone, my name is Dilip Kumar Mishra, a PhD student in the School of Electrical and Data Engineering at University of Technology, Sydney. My supervisor is Dr. Reddy. Currently, I am working on the research topic of resilience quantification, and today I will be talking about a novel approach to quantify the resilience of active distribution network. Coming to my introduction slide, if as I am working on the resilience domain, so the term resilience will come into the picture when there is an unpredictable and unforeseen event like bushfire, storms, and any extreme event that lead to power outages, which directly impacts an economy as well as life. Like huge economic losses will be there and life threats are increases. We should not run away with this kind of situation, but we should build a system that can quickly cope with extreme events and restore normal operation. That is what it is called resilience. And resilience is somehow related to the reliability, only considering the event, like it is low impact and high probability event for reliability. And for resiliency, it is high impact and low probability. Moving to my next slide. Several authors have developed their resilience statistics in different form, like triangular form and trapezoidal form. And one of the author, he described the functionality level in terms of robustness and rapidness. So here, once let the disaster happens at this point, and it will start the degradation process. Here, the robustness is decreasing, as you can see here. Then the restoration process will start, and if it will be faster, then the resilience will be high. So considering the trapezoidal form, so they have described in three different phases for disturbance, emergence, and restoration for phase 1, phase 2, phase 3, respectively. And this is my proposed one. So this is the traditional system and this is the resilient system where I have considered 5 different phases A, B, C, D, and E. Considering the A, if we have enough resources like number of distributed energy resources like PV plus large battery, even during the event, the system can cope against some of the critical load maybe. And by using the diesel generator, the emergency coordination time, the some of the critical load can, it can resist some, up to some extent. Then we will go for the reconfiguration part, and with the help of reconfiguration, that the placement of tie line with the optimal placement of distributed energy resources, some of the critical load can be restored. If the disaster, the magnitude is very high, multiple fault happens, then we can go for the mobility services like mobile substation, mobile storage unit. As far as the mobility service is concerned, so definitely it will take some time to reach to the load center, and once it will reach at the load center, and it will start the restoration process, and which is called E phase. A, B is the one. A for traditional system for recovery, B is for resilient system for recovery, and 1 and 2 is the withstanding capability, and adapt means the stability part should be there, and prevent means preventive the power system collapse. So these 4 major attributes are extremely important, like withstand, recover, adapt, and prevent element. And each attribute has its significant value, like withstand, increasing the self-healing capacity, recovery talks about the restoration part, adapt means the stability part, and prevent means the preventing the power system collapse. Here I have developed 4 different resilience, indices of RW, like withstand, recover, adapt, and prevent element. In my research, this is based on 2 main. One is the quantification of resilience, another is enhancement of resilience. The quantification can be done like it defines the impacts on event, like cost benefit analysis, image of risk. For the enhancement part, there are several, the combination of resources can be used to enhance the resilience of the system. That means more renewables, the virtual power plant, mobility services, and many more. So I have conducted a case study. So in IEEE 33 bus test system, so these are the 3 different scenarios I have created. In scenario 1, only storage available. Scenario 2, PB is available. In scenario 3, both are available. And this is the system data. For scenario 1, due to the storage capacity, maybe the limited capacity, the system, with the help of storage capacity, the total amount of critical load cannot be restored. So the mobile energy storage unit can go to that place, and it can the system, all the critical load can be restored. Then for scenario 2, the PV is available, at least some, it is definitely it will have some more capacity as compared to the storage one. So only 2 energy storage, mobile energy storage are required to restore the critical load. Considering the scenario 3, we have both PV and storages, and it is having the sufficient capacity to meet all the critical load. Here, resilience improvement graph, like for the withstand, recover, adapt, and prevent element using different combination of resources like microgrid plus tie line plus MSU. The here I have considered one level is resilience, another is the risk. If you want to increase the resilience level, then the risk level will be minimized according to the economic losses. So the proposed research is significant because understanding the quantification of resilience is vital. It can contribute to energy master plan for changing the energy landscape, considering the natural disaster and cyber attack. So resilience is an emergent property of a system which changing the boundary condition. Every time it is changing, thus building a resilient system which increasing the origin which can save the world from deficiency. One is economic loss and one is life threat. So two things are very important nowadays. One is ignition. We need to ignite our energy industry. Now then we will go for the transition part from reliable to resilient part. Thank you very much.